Hey, this is Graham Werner. I'm going to be doing just a quick presentation of our System Dynamics project. What we did was we heated an aluminum block under multiple conditions that I'll describe here in a second. So our objective was to heat a block that came out of the freezer, and we'll have all convective heating due to room temperature air, and then we have convective heating due to room temperature air, and a flow rate of water that passes through a through hole right in the center of the block. What we needed to validate first was that we had a Biot number that's less than 0.1, so we can use the lumped capacitive approximation where there are no temperature gradients as a function of position in the block. Our hypotheses were that we could use the lumped capacitive approximation, and that in either case, where we have just convection due to air and then convection due to air and water, that this system dynamics models will be effective at showing the general behavior of heating over time. And what we expect to see when we actually perform the test and when we model the test is to have something that resembles Newton's law of cooling. So here's first what we did was we found the Biot number for convection due to only air. So we've got multiple values for our convective heat transfer coefficient here between 5 and 10. So we went and we calculated the Biot number. So we had between 0.003 and 0.0059 for air, which leads us to assume that we won't have any temperature gradients as a function of temperature. No temperature gradients as a function of position inside the block. But we just wanted to validate that. So we took the block out of the freezer, and over the course of 100 minutes, we measured the interior temperature and the exterior temperature of the block. So in red here, we have the exterior temperature, and in blue, we have the interior temperature. And what this tells us is there's no great disparity in these temperatures, so we could assume that we won't have any temperature gradients inside of the block itself. Next, we created a model. This is a second order dynamic equation for the convective heating of the block. This is our unique solution where we factor in the initial temperature of the block, and we've got our TB term, which is our forcing function in this case. We've got a resistance and one capacitance because we've got one block. And we can look at its time-dependent behavior. This is just our setup. So we had the block, we had 4 legs screwed into the block, so we allowed convection on all surfaces. And this is our experiment. So over the course of 300 minutes, we observed this curve here, which pretty much models a decaying exponential, which is what we expected. And we heated the block from an initial temperature of negative 2.2 C all the way up to 17.7 C. And then we went and we created our theoretical models. So like before when I said the free convective heat transfer coefficient of air varies, so what we did was we created two resistance values, an R high and an R low, based on these two H values. So in the case of R high, we have this dotted red line. And then in the case of R low, we've got this upper dotted red line. So we see that with these two approximations, our actual results fit somewhere in the middle, which is what we would expect. So this is our transfer function where we have temperature of the block as a temperature, or as a function of the temperature of the bath. And this is a second order equation where we have these characteristic roots. We've got our state space and state equations, and we've got our theoretical accuracy. So like I said before, So yeah, we have our expected behavior, and it's actually really gratifying that we were able to nest these experimental results in between the two theoretical curves. And then we moved on and we created a model for the situation where we have free convection due to air, and we've got forced convection due to flowing water through that through hole. So after some simplification, we arrive at our system solution, and this is our unique solution. And we've got two resistances. We've got the thermal resistance due to air, and we've got a thermal resistance due to water. So we went and tested. What we did was we took the block right out of the freezer and put it on the sink top. We flowed a consistent flow rate of water through the through hole, where the bottom of the through hole is partly obstructed. And what we did is about every 20 seconds we stuck this type K thermocouple into this hole here, and we measured its temperature. So this is our resulting curve. So we see again that we're kind of closely modeling Newton's law of cooling with our decaying exponential with an R-squared value of 0.998. So with a fair degree of accuracy, we can say that we collected some good results. We've got an initial air temperature of 21 Celsius, a water temperature of 25 Celsius, and an initial block temperature of 0.3 Celsius. So this comes into play when we model our system theoretically, where we know that we have initial conditions and our forcing functions. And we followed the same process as the case where we just have convection by air, where we're able to create two different resistance values. So we'll have two different responses, where we have an H value of 6,000 watts per meter squared Kelvin and an H value of 2,000 watts per meter squared Kelvin. And we just pulled those values off of Engineering Toolbox. The issue is the forced convective heat transfer coefficient varies so much because you've got different surfaces in contact with different geometries, different flow rates, and the coefficient even changes at different temperatures. But all in all, we have the same type of behavior here, where we've got this over-damped response, and we see that our experimental results still nest in between these two theoretical curves. So these would be our transfer functions again, except now we have two different inputs to the system. We've got temperature of the air and temperature of the water. And you see in either case that we'll have the same denominator, and we have no numerator dynamics. The characteristic equation roots are 0 and R1 plus R2 over CR1 R2. So we've got two real distinct roots, so we can say that our system is overdamped. And then in either case, we can validate that. Here's our state space and state equation. And then this just summarizes the accuracy. And that's it. I hope you enjoyed the presentation, and feel free to scroll back through it if you missed anything or if I missed anything.